and we should move this through this part of the topic, or this topic, reasonably quickly. And so I'll feel more comfortable towards the end of this term. We're in week 6 now. We've got, so that means we have 5 weeks to go, is that right? 6, 7, 8, 9, 10. Yeah, 5, including this week, we have 5 to go, which is good. Looks like we're on track to be at a point at the end of this term where I'll be comfortable that we can finish the course, no worries, before the end of next term. Maybe even have a little bit of revision at the end of next term. Okay. Electromagnetic radiation. What is? Oh, actually, I'll do an introduction first, and should I? I suppose I should record this. So, what is light? It is a wave. Yep. Shh, please, people. Those people talking. Thank you. So light is waves and particles. So what we call that is the wave particle nature of light. Yes, we have experience in our lives of, and I'll say light, and you guys all say, well, that's the stuff we see with. That is light. There's other forms of light as well. So we call that the visible spectrum. Ultraviolet light, which we can't see, but we can experience. Our cells can experience ultraviolet light. How do they experience it? You don't necessarily feel it. Yeah, you do. Yeah, burns your skin. Essentially, changes, causes the energy in the cells that make up your skin to increase so much that they cook, essentially, and also ultraviolet light has sufficient energy to change the DNA structure in cells, which is really dangerous. You, Yeah, that's when we can get cancer. Yeah, so if you put your hand under ultraviolet light for a long period of time, the more exposure you have, the more chance you have of causing cell damage. Cell damage happens with the burning as well as cell damage at the DNA level. The DNA damage is particularly dangerous. Remember that DNA is just a chemical. It's made up of atoms and it's in that spiral shape, the double helix. So it's just a chemical. The frequency of ultraviolet light, the energy of ultraviolet light is sufficient that that as it comes through your skin, it actually penetrates. It can penetrate, and it might change the chemical nature of the DNA in a cell. If it does that, and it will do that often it won't have any effect whatsoever. It'll just the DNA will, the cell might die because it doesn't replicate itself. In unfortunate circumstances, though, sometimes whatever part of the chemical it breaks off or damages is part of the instruction for mitosis, or the new cell. And if we get if you get this damage which causes mitosis to become uncontrollable, so it just keeps replicating itself, that cell, then we have cancer. Cancer is particularly hard to treat because it's your own cells, so your body doesn't know that there's anything wrong at all, and that's why it's so nasty. Your body doesn't fight it. Anybody that says, I know somebody that recently that died of cancer and went and prior to that, obviously, went and had some treatment where they had vitamins. They had these big vitamin supplements, very expensive, one of these radical therapies where you take on lots of really good vitamins, so to speak. What's wrong with that, do you think, from what I've just described of cancer? It doesn't work, though. All it's doing is giving you extra nutrition. If it does work, if it does give you extra nutrition, it gives more nutrition to your good cells as well as the cancer cells. And what happened was the cancer spread even more rapidly because it was getting everything that it needed. Okay, so there's not a lot known about cancer, and there's also a lot of people that think that they can treat cancer with these radical therapies, and they are just not a good idea. Some, of course, might be good. We don't know. You'd have to look at the studies of that sort of thing. But So yes, UV, ultraviolet light, which we can't see but we can experience, our cells can experience, our biology can experience that in a certain way, which is not necessarily a good thing. Yes. Black light will have the same effect. Yeah, it is ultraviolet light. In fact, the we we sit in here. These fluoro globes here, what they do is we pass electricity through those globes and through that glass, and inside there is mercury. Little drop. They put one tiny little drop of mercury in there, and that vaporizes in that low pressure environment, and they pass electricity through it, and the mercury itself emits ultraviolet light. We don't experience ultraviolet light out here. Why is that? Has anybody ever broken one of those things? What does it do? There's white powder inside, yes, and it explodes, doesn't it? Well, it actually implodes because there's a reduction in the air. So it's a little bit of a vacuum inside. So when you hear it, it actually it it's the air rushing into that space. Okay. Yes, it would be too. Yeah. So and that's phosphorus, I think, is the coating, is the white powder. What happens is the UV light hits the phosphorus, which is coating the glass, and the phosphorus is the thing that emits the light for us. And that's complicated. We'll look at that later. So we're not sitting here bathed in UV light. The phosphorus reduces the energy to visible light for us so that we can use it. Um, that's UV. What other types of light are there? Yeah. Yes. Infrared's the first one. We can experience infrared instantaneously. What is that? It's heat, yeah. So we can't see it, but we can experience it as heat. Okay, our cells react to it by, or the molecules that make us up vibrate faster, and so we perceive that as heat. Uh, X-rays, X-rays, we wouldn't know until after a very long time. The X-rays would do damage to our cells, DNA damage. That's why when you go and get an X-ray, they put lead over every other part of your body they're not interested in, because they want to protect you from that light as best they can. Yes. Night vision. Yeah, night vision is basically uses it's a light amplification system. So it takes the light that is there, and there's almost always light from stars and the moon and that sort of thing, and takes that, amplifies it so that you can see. If you go into a cave, if you ever been into a cave and they switch the lights off, night vision would not work, or that type of night vision would not work because there is no light. Your eyes never adjust to it. Yes, that's right. That's different. So there's a yeah, heat vision goggles which would show areas of, or relative areas of warmth compared to cool. Yes, and so human bodies would look warmer than the area around it, so you could see that way. Infrared sensors, that's right. Uh, yeah, they're good. They're very expensive though. Uh, Gamma radiation, yes, gamma radiation, higher energy again than X-rays, higher than UV, higher than X-rays. Gamma radiation is pretty nasty. We experience that as radiation from radioactive substances. We'll go into that again in a later topic as well. Um, there's also, somebody mentioned the other day, cosmic radiation, which is radiation left over from the Big Bang, and radiation that we receive from stars. Lucky for us, we have the Earth magnetic field to deflect a lot of those charged particles away. Yes. Yeah, so the higher you are up in our atmosphere, our biology, of course, is has evolved to live at surface level on this planet. So you can feel the air here, and the air is a big protector. It's like a big blanket that stops us from getting damaged from a lot of those things that come through. And so if you go up to 30,000 feet, which is about 10 kilometers, then you're actually going up higher in the gas, and as the higher you go, the thinner it gets. And so you might find a lot of pilots experience eye problems because of the higher incidence of UV radiation at that altitude. Okay, unless they wear special glasses. Hi. Uh, there's also microwaves, light. We use that to, yeah, to heat food up, and essentially what it does, all food has water in it, and what the microwaves do is they go through and they cause the water molecules that make up your food to vibrate, and of course that vibration causes heat, and so it's a good way to heat food. Um, heats up the what? Heats up the plate. Yeah, I always wondered about how it heats up plates. I don't know anything about that. Because how much water would be in plates, do you think? I guess it causes the molecules in any substance to vibrate a little bit more than. Yeah, that's right. So, yeah, not so much, not as much as it is if you use infrared radiation to heat it up. So often, yeah, often you put something in the oven that's very cold, and you pull it out, and it's really hot on the outside, and you stick a knife in it, and it's cold inside. I always touch it to my lips to feel the temperature. Um, Yeah, that's right. Whereas microwaves don't, that doesn't happen so much because the microwaves actually penetrate better than the infrared radiation of your oven will. Okay. What's that? What? Yeah. Yes. Was it? Yeah. Okay. You should stir it occasionally. Have you heard that term? Stir occasionally. uh, and then there's one other light that we experience all the time. We're being bathed in them at the moment. The radio waves. Yeah, radio waves. And that's just light. Metal in the microwave. Yeah, that's an interesting thing. Uh, it was ice cold. Yeah. Yes. I actually don't know why it does that, to tell you the truth. Mm. Yes. Yeah, I have seen it before. I forgot that I had a spoon in a bowl once years ago, and and the, and I switched it on. And yeah, that's right, alfoil, and walked away, and I heard all these little bangs going on, and I looked inside the microwave, and there were sparks flying everywhere. There's all sorts of crazy stuff you can do with microwaves if you YouTube. Yeah. He was Danish. He said that electric currents will produce magnetic fields. And we've just spent some time doing this. If I if I have a wire and I pass a current through it, there will be a magnetic field associated with that current. If there's no current, no magnetic field. Okay? And so this guy, Hans, he first described it. Later, still in the 1820s, um, Andre Marie Ampere. Yeah, you might know that one. He was French, and he noticed and described. No, Tesla. Yeah, interactions between electric currents. So this, and this of course led to, how is it that electric currents interact with each other from a distance? If I had two currents in two wires, how are they going to interact with each other? Well, there's the magnetism that results from that current traveling through that wire will interact with itself, and so they didn't see the magnetic field at this point. Oh, sorry, they didn't perceive that it was the magnetic field causing it at this point. 1830s, so very short time after this. Michael Faraday. Yeah, you'll have heard Faraday's law. He was English, and he looked at EM induction, electromagnetic induction, which is that electric fields induce magnetic fields and vice versa. Yeah, okay. 1860, so we get a little bit later, and this isn't that long ago. Yes, okay. As far as physics, this is very recent physics as far as physics goes. James Clerk Maxwell. James Maxwell, he was English also. Changing magnetic fields produce currents in conductors. What's that, Josh? Yeah, I'll talk about that in a second. So just let me finish this sentence. And so electric fields. And this guy actually came up with a set of equations. I won't show them to you. They look very simple, but they're quite complicated. And if you go on and do physics at university, then you'll spend a lot of time with the Maxwell's equations. He's basically, for the first time, he's unified magnetism, electromagnetism, and light, and shown that they're very, very closely related. It's a unified theory of electromagnetism, okay? And he described it mathematically as well. So groundbreaking. James Clerk Maxwell. I'll show you a picture of him very quickly. If the internet's fast enough, it might not be. I'm going to give up. Oh. James Maxwell. There he is there. I don't think he didn't live very long. He was only 48 when he died. Yeah. So he had a big beard. They liked their beards back then. Yep. Okay. Hmm. Oscillation of electric currents. If I can cause electric currents to oscillate back and forth, and I can do something, I can make light. How is it that we make light? So have a look at this idea here. Let's take a conductor looking like this, and what I'll do is I'll say that at this point is A, at the center is B, at the other end is C, and what I'm going to do is I'm going to cause an electric charge, a charged particle. We'll just look at one. In fact, it's very rarely one. Or in fact, it's probably never one, actually. We'll just imagine that it is one electron. And the electron is oscillating backwards and forwards down this wire. How would it do that? We might make it separate wires, okay, and connect it to what is called a alternating current generator. So what this will do is if we alternate between positive and negative on either side, we'll get the electrons all go to this end, and then the electrons will all go to this end, and the electrons will all go to this end, and so on and so forth. And they'll do that if this thing is very good with regular period, okay, with a regular oscillation backwards and forwards. At what point does it have maximum velocity? At B, yeah, okay, so maximum velocity there. Maximum velocity. At what point is there, are they stationary? A and C, aren't they? So momentarily stationary. And in between, what's going on? Well, they're moving through here, and then they're accelerating, aren't they? And I'm going to say accelerating. You'd be inclined to say decelerating. Yes, they are. They're slowing down, but I'll just say that it's acceleration. The charge is accelerating, which means that its velocity is changing down to 0, and then accelerates back up again to maximum velocity, starts slowing down to 0, back up again to maximum velocity, and just keeps doing that. You can imagine. Okay? Where's the maximum acceleration? In here? What do you mean right at the start? Yeah, the moment that the electron turns around is maximum acceleration. Maximum acceleration at these 2 points. Okay. Where is its acceleration 0? B. Somebody say D. Acceleration 0. Just for a moment, the acceleration would be 0 momentarily. Okay. So you understand that. That's fine. If I want to make an electric field, I have that situation, and let's look at the same thing here, except I've put it in a different orientation. There's A and there's C, and I have these electrons oscillating up and down. Okay, so they're all up this end at one point, and the next moment they're all up this end. And so at this point here, there'd be lots of negative over here and lots of positive over this side. And then when they're down this end, there'd be lots of negative down here and lots of positive on this side. What they tend to do, if they oscillate, what they will do is create an electric field. Okay, so you can think of an electric field. Actually, I'll do it this way. In the same plane as the original wire. So they'll oscillate, they'll accelerate, and it will cause this creation, this electric field. In the same plane as the oscillating electrons. If I have a changing electric field, does anybody know what else I will have? Yeah, changing magnetic field, won't I? So in this situation, a changing magnetic field would look like this, and my drawing won't be very good. It's going to be at at right angles to that electric field. Okay. At right angles to the electric field, we have a magnetic field. Oscillating. Okay. If I have an oscillating electric field and an oscillating magnetic field, and they're oscillating because of each other, they're self-propagating. If I have a changing electric field, then I have a changing magnetic field. Okay. We have what is called light or EM radiation. This is so I want you to know that the electric field oscillates in the same plane as the oscillating charges. The magnetic field oscillates at right angles to that. And that at right angles to it is the direction of the velocity, at right angles to both the electric field and the magnetic field. The velocity is in this direction, V. Are we out of time?